Myself, Jivi and Dr. Kiran Yadav. In this session, I will discuss about the origin of quantum mechanics. So, this is a famous book for quantum mechanics which you can refer for your studies. It is Quantum Mechanics Concepts and Applications by Duality. Okay, so you can refer this book for your MSc syllabus, and there is another book by David J. Griffith which is also quite good. So these are the some of the famous scientists which contributed in the development of quantum mechanics. These are Dirac, Planck, Hertz, Heisenberg, Schrödinger, Bohr, Compton, de Broglie, and Feynman. So these are also scientists which contributed in the development of quantum mechanics. So let's see the history and how quantum mechanics was originated. So in the end of 19th century, physics was basically classified into three different branches. First was the classical mechanics, second was the electromagnetic theory, and third was the thermodynamics. In classical mechanics, dynamics of material bodies was studied. In electromagnetic theory, radiation, matter in terms of particle, and radiation in waves were studies. In thermodynamics, interaction between matter and radiation were studied, and the ultimate goal of studying physics was to describe the nature. In the beginning of 20th century, classical physics seriously challenged on two major fronts, and the validity of classical physics ceased at very high speed and at microscopic levels. So the objects at very high speeds are said to be in relativistic domain. Einstein's 1905 theory of relativity showed that the validity of Newtonian mechanics ceases when the particles travel at very high speeds, when the velocity of the particles is comparable to the velocity of light. Some newly discovered phenomena such as which are of atomic and subatomic structure. In such phenomena, classical physics fails to explain them. Okay, so these were the two major phenomena or two major incidences where the classical physics failed to explain, and that new concepts had to be invoked to describe, for instance, the structure of atoms and molecules and how light interacts with them. So these failures of classical physics incited the scientists to discover some other branch of physics, which was quantum mechanics. So classical physics basically failed to explain microscopic phenomena like blackbody radiation, photoelectric effect, Compton scattering, atomic stability, atomic spectroscopy. So after that, in 1900, quantum theory came into picture. Okay, so in quantum theory, energy exchange between radiations and its surrounding takes place in discrete amount, or we can say that energy is quantized. Energy exchange between an electromagnetic wave of frequency nu and matter occurs only in integer multiples of h nu. So the formula for E is nh nu. Here h is Planck's constant, nu is the frequency, and n is any number whose value can be 1, 2, 3, 4, or I can say it is an integer. So the energy of photon is equals to h nu in quantum mechanics, and energy of a particle cannot take any continuous values. There are only certain specified values which a particle can take for energy. Planck's quantum theory provides an accurate explanation of blackbody radiations. It also explains photoelectric effect. Theoretical support was done by Einstein in 1905. Quantization of electromagnetic waves is valid for light also. So light itself is made of discrete bits of energy called photons, each of energy h new frequency of the light. Now, Rutherford's discovery of the atomic nucleus in 1911. Basically, he did a alpha particle scattering experiment where he took a gold foil and scattered alpha particles, and in that experiment he discovered atomic nucleus. Bohr model of hydrogen atom was given in 1913, in which he said that atoms can be found only in discrete states of energy. Interaction of atoms with radiation, that is the emission or absorption of radiation by atoms, take place only in discrete amount of energy. It explained the atomic stability and atomic spectroscopy. In 1923, Compton scattering confirmed the corpuscular aspect of light. Due to Planck, Einstein, Bohr and Compton gave both the theoretical foundation as well as the conclusive experimental confirmation for the particle aspect of waves. Waves exhibit particle behavior at the microscopic scale. So this concept is generally called as wave-particle duality, in which it is said that a particle can behave as a wave or a particle, depending on the phenomena in which we are studying it. At this scale, classical physics fails not only to quantitatively but even qualitatively and conceptually. T. Broglie in 1923 not only does radiation exhibit particle-like behavior but conversely, material particles themselves display wave-like behavior. Confirmed experimentally in 1927 by Davison and Zermer. Postulate of Planck and assumptions of Bohr lacking the ingredients of a theory. Do not follow from the first principles of a theory. Need to fit them without the context of consistency theory led Heisenberg and Schrödinger to search for the theoretical foundation underlying new ideas. By 1925, validate the various experimental findings as well as Bohr's postulates into a refined theory quantum mechanics or old quantum physics. This provided an accurate reproduction of the existing experimental data. Theory turned out to explore and unravel many uncharted areas of the microphysical world. So this is how the quantum physics came into picture. So this is it for this session. In the next session we will further continue our discussion. Thanks for your attention.